Hello, everybody. Welcome to lesson 6.4. Today, we're going to be talking about the method of disks and rings. So this is going to be another method for finding volume, specifically volume for solids of revolution. A solid of revolution is something that's created by rotating around an axis. So let's get cooking, looking at solids of revolution, how to find their volume using these methods. So the method of rings or the method of disks, basically the idea here is I'm going to create a solid of revolution by taking a function and rotating it around an axis. So what I've done here is we're going to take this function, we're going to rotate it around the x-axis. And if I do that, rotate that around the x-axis, then inside of right here, this is going to create a solid that looks something like this over this interval from A to B. So this is going to be, looks like this kind of vase looking shape. And our goal is going to be to find the volume of this solid. All right, so since our goal is to find the volume of the solid, we can find it in one of the two following ways. It's either integral from A to B of AX dx or integral from C to D of AY dy. Basically, all this is saying is I need to integrate over the bounds where A of X or A of Y is the cross-sectional area of the solid. So cross-sectional area means kind of like we looked at in the volume from cross-sections last time. Cross-sectional area means if I were to take this thing and cut it perpendicular to the x-axis, I would need to find some kind of equation that could give me the area of this one cross section. And then if I integrate over the integral from A to B, just like we saw in that last video about volume from cross sections, integrating from A to B, if I have this equation for area, would give me the volume of this solid. So today we're going to look at how to do that using what's called the method of rings. So I notice right here, if I were to cut perpendicular to the x-axis right here, then this shape is going to create a circle. So, which means the area of this circle is pi r squared. Pretty straightforward. So if, and we'll take a look a little bit later at what it would look like if there is actually an inner circle, like a circle inside of a circle. But basically the idea here is for the method of rings, we're going to do outer radius squared minus inner radius squared and then times pi. That's the area. Because I'm basically taking the big circle, subtracting the smaller circle. In this case, there is no smaller circle, so I wouldn't have to worry about that inner radius. But I want to go ahead and give you this equation so that you can see what this is going to look like when you use it. So this is the method of rings. So let's take a look at an example. So right here, we're going to find the volume of the solid taken or found by rotating this function around the x-axis. And it's going to be bounded by these values 1 and 4. So first I want to get kind of a rough sketch of what this looks like two-dimensionally. I notice here, I'm going to run through this pretty quickly because I assume that you know the algebra. The discriminant of this is negative, so it never actually hits the x-axis. The vertex happens when x equals 2. So if I'm bounded by 1 and 4, this is also opening up. This is going to look something like this. In fact, this is probably, it is, this graph from the first page right here. All right, so if this is bounded from 1 to 4, what I'm going to do is I'm going to take this and rotate it around the x-axis, and I'm going to create a solid that looks something like, I'm going to try and draw this to the best of my ability, a solid that looks something like this that we just saw on the previous page. So it's going to look something like this over here on the back part. There's another little rounded part right there. So this solid is going to look something like this. So what we're going to do is we're just going to set up the integral. So I want to do the integral from 1 to 4. I want to do A of X. The reason I'm using X in this case is because since I'm rotating around the x-axis, when I look at my cross sections, I want to cut my cross sections perpendicular to the x-axis. So like we saw in the last video, whichever axis my cross sections are perpendicular to, that's what I'm going to integrate with respect to. So if I'm rotating around the x-axis or anything parallel to the x-axis, meaning if I would rotate around like y equals 4 or something like that, then I'm going to do dx in this integral. So I know that this is going to be pi times this because pi is the constant that is in the area of a circle. So what I want to do is I want to look for the outer radius. So in this case, if I were to draw one just cross section of this, so something like this, the outer radius is going to be the distance from the x-axis to this function. So the outer radius is actually just the function itself. So the outer radius is x squared minus 4x plus 5 squared. So that's the outer radius squared minus inner radius squared. In this case, there is no end radius because there's no other function. So that's, I'm just gonna do 0 squared right here so you can see what that looks like. No reason to actually include that when you're doing this yourself. I'm just doing it here to show you that I'm putting 0 because there is no inner radius in this case. And then this is gonna be dx. So now I'm gonna leave it up to you to actually find that integral. So if you have any questions, make sure that you bring them to class about this problem. We're going to do this problem and the next problem we're about to do in class first, and then we're going to do more example problems of the method of rings. All right, so for the second problem, we're going to take a look at this and say, all right, we're going to determine the volume of the solid obtained by rotating this portion of the region bounded by cube root of x and x over 4 that's in the first quadrant around the y-axis. So what's going to help is first, we need to figure out what this looks like in the first quadrant. So cube root of x is going to look something like this. And then x over 4 is going to look something, I'll do it in a different color. It's going to look something like this. So the question is, I just drew a rough sketch right here. I don't know if I actually have my upper and lower function correct, but what I'm doing here is I'm rotating. I'm going to get rid of this portion that is not in the first quadrant, because that's not what I'm rotating. I'm taking this area right here, so this purple part right here, and rotating it around the y-axis. So what I'm going to get is a solid that looks something like this all the way around. So it's going to be circular. It's going to have like kind of a little hole inside of it. It's going to look kind of like a vase that you can reach down inside of. And when I'm finding the volume of the solid, one thing I also want to point out, I'm finding the volume of the actual solid, not including the volume that it can hold. So I just want the volume of the solid itself. And when we get in class, we'll look at some better pictures of this because I'm not the greatest artist. But basically what's going to happen here, it's going to have just kind of a solid shell around the outside and then a little bit of a hole in the middle of it. So we're going to have to try and figure out, basically, first thing I want to notice is I'm rotating around the y-axis. Since I'm rotating around the y-axis, I want to use dy. So my integral, this is going to be pi times something and then dy. All right, so when I'm setting this up, in fact, I'm going to give myself a little bit more space here, just in case. So when I'm setting this up, what I want to think about, in order for me to set it up, I need the bounds, I need the outer radius, well, I need the right function, I need the left function. So first, I notice these are written in terms of x. I want them in terms of y because this is going to be dy. So instead of y equals x to the 1/3, I'm going to write this as x equals y cubed. And then instead of y equals x over 4, in fact, here, let me do it in different colors to correlate with what we have in the graph. Instead of y equals x over 4, I'm going to write x equals 4y. So I need to do a little bit of algebra here to help me find the bounds and also figure out which one is my right function, which one is my left function. So in order to help me find the bounds, I need to set these two things equal to each other. So I need to say, let me do a different color, y cubed equals 4y. So hopefully you can look at this and say, all right, so then y equals 2. All right. So y equals 2 or -2, but -2 really doesn't matter to us because we're in the first quadrant. So the bounds here, I can also see they intersect at 0. So this is 2, -2, and 0. -2 is not relevant for us because we're only looking in the first quadrant. So the bounds here are going to be from 0 to 2. Now I need to identify my right and left function. In order to do that, one easy thing to do would be just take the number 1. So take the number 1 and plug it into each one of these. The reason I'm taking the number 1 is it's between the bounds 0 and 2. So whichever one is greater between 0 and 2 should be my right function. So if I plug in 1, right here I get 4, right here I get 1. So this is my right function. And then this will be my left function. So then my right function, remember we're doing all this dy. So my right function, this would be 4y squared minus my left function, which would be y cubed squared. Now I've got my integral set up. And again, I'm going to leave it up to you to actually find that integral. So that was a lot of information thrown at you today. I'm aware of that, but we're going to do plenty of class. basically our main topics today were defining what a solid of revolution was. And then we talked about the method of disks, method of rings. They're one and the same. The method of disks is just the method of rings when there is no inner radius. So if you have any questions, bring them to class. I hope you took some notes, and I will see you in the next video. Have a great day.